Break, guys. This is chapter 8, lesson 1, and we're going to do our normal 2 problems about describing rotational motion. So our first problem reads, a disk of radius 5.7 centimeters rotates around its axis, and a point 1.9 centimeters from the center of the disk moves 34.5 centimeters in 12.2 seconds. Calculate the angular speed of the disk. So we found out yesterday that angular speed is equal to RW. And we have 2 equations involving W that we could possibly use. The first one being W is equal to change in theta over change in time. And the other one being that velocity is equal to the radius times W. So I need to find my angular speed. I get a couple numbers that don't really matter. This number does not matter because that's the radius of the entire disk, and we are focusing on just the point right here. So that is a radius for me, and I'm going to convert that into meters, so that's really 0.19 or 0.019 meters. Then I'm also given a distance that it moves and a time. Now, one of the problems is they did not give me the angle that it moved, or the theta. So I'm going to need to figure that out. But I do have over here V. So I can't use that because I don't have theta. But over here I know V. And if you'll remember back to, I think, chapter 2 or 3, we know V is equal to d over t. So I could find out that if the disk moves, and again I'm going to convert that to meters, 0.0345 meters in 12.2 seconds, that can tell me my velocity. And that would tell me that it was moving at 0.0283 meters per second. So I know velocity is equal to R times W. So if I want to just find W, I would need to divide both sides by R. So I'm going to take this and I'm going to divide by my R of 0.019, and that will give me 1.49, and then W is measured in radians per second, and that is W, and W is equal to angular speed. So I'm good. And then here's our second question for the day. Second question says, a grindstone has a constant angular acceleration of 0.27 radians per second squared. Starting from rest, what is the angular displacement of a point on the wheel during the interval of t equals 0 to t is equal to 9 seconds? So one of the reasons I chose this one is because we have to combine some of our old equations with this new equation. It's not that bad. So when we're trying to find displacement, we could call that, in a different chapter, we would have called displacement our final position. And we remember that our final position is equal to your initial position plus your velocity initial times time plus 1/2 acceleration time final squared. If that one's not, if you haven't memorized that one yet, then I don't know, you might not have been doing your homework. Richard/Austin. So here we don't have an initial position. We could say that our final position, because we're going around in a circle, is just our change in theta. So we're going to say that our theta, and we're not talking about velocity, but we're talking about our angular velocity times time. And then just like we're talking about angular velocity instead of angular acceleration, instead of our normal acceleration, we'll have our omega acceleration times time squared. So It says it's starting from rest, so the nice thing we know is this is going to be 0, so I can forget about all that. And I can know that theta is going to be 1/2, and I am told my acceleration up there, so 0.2. I can erase now. That was a lot of erasing. I'm sorry. Okay, let me retry that. So we have is equal to 0.27, and I'll rewrite this. 0.27 radians per second squared times 1/2 times time squared, and my time is 9 seconds squared. So 9 times 9 times 1/2 times 0.27 is going to be equal to 10.9, and my answer here is in radians, because we measured change in theta in radians. So you could just be down there and say 10.9 radians. You can do a little math and know that 10.9 radians is equal to 624 degrees, or 1.7 rotations. Any of those answers would be fine. I hope that my writing was a little bit better. I know that I messed up with the eraser, but I have this fancy new pen, so that's kind of cool. And hopefully I'll get better. I can even like sign my name, and yes, my signature is always that bad. But yeah, have a good Friday, guys. Enjoy your weekends.